Hello, everyone, and welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Stacy McGaugh with us today. Hello, Stacy.
Hello.
Hi there. And it is December 2nd of 2024 as we record this. And Stacy, what's your geolocation? Where are you at?
I am in Cleveland, specifically Cleveland Heights, which is a suburb of Cleveland, Ohio.
Very cool. And it is after Thanksgiving in early December. So do we have snow on the ground in Cleveland yet?
We do. Where we are, looking out the window now, it's just now covering the grass.
Cool.
To my east, people have gotten 2 or 3 feet, 30 miles from here. There's a
Oh, on the lake effect, like a lake effect snow.
Yes.
Yeah, yeah,
And there's a very well-known steep gradient from the west side to the east side. So the west side of Cleveland gets very little in the way of lake effect, and the geography and the prevailing winds are such that the east side gets more. And so as I travel from my campus at Case Western on the eastern edge of Cleveland proper to my home, couple miles east in Cleveland Heights, I can tell
yeah,
there's more snow here. And then my wife works at John Carroll University, which is a few miles further east. And again, you can tell the gradient. So it's a
yeah.
very pronounced localized effect.
Did not know that about Cleveland. I did live in Chicago for a better part of a decade, so I'm a little familiar with the lake effect snow, but I didn't think the gradient was so sharp in some places. So it's pretty cool. Good. And Stacy, what do you like to do for research?
Well, I work on galaxies and everything extragalactic, including cosmology and the big picture sort of things. And so I've become, well, I started as a surface photometer. I love the distribution of stars, mapping out, the gradients, and especially worked on low surface brightness galaxies,
Yeah.
which is sort of what led me to the topic of today's subject. That and the kinematics of galaxies, how
Yeah.
things move. I was fortunate enough to be postdoc with Vera Rubin for a while, and she
Very
was always
nice.
very keen on not just where things were, which is sort of what we're mapping with surface photometry, but how they move. And so that whole phase space is what interests me.
Very cool. Nice shout out to Vera. Very good. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. Go grab a copy for free. Accelerated structure formation. The early emergence of massive galaxies and clusters of galaxies. And Stacy, take us away.
Well, so first I would like to acknowledge my co-authors, Jim Schomburg at the University of Oregon, who's been a collaborator for many years now, Federico Lelli at INAF in Arcetri in Italy. He was a postdoc here for a while.
Mm-hmm.
And Jay Frank, who was a graduate student here, he took the route of going into industry after
Okay.
graduating.
Mm-hmm.
But some of the foundational work of this paper was part of Jay's thesis, and this paper wouldn't exist without his work. So
Very cool.
a
Great
big
shout
shout
out.
out to him.
Great shout out. Okay, let's get into it.
Okay, so I think, well, the topic now is to do with how galaxies form and when. And as astronomers, we're always obsessed with that. We see stars, we see galaxies, and we want to know how they came to be.
Indeed.
And, a lot of times what we observe tells us a lot about what they are now. It's a little harder to figure out how they came to be.
Mm-hmm.
So star formation is still an ongoing subject of research, even as we
Yes.
think we mostly understand stellar evolution. Galaxies are more of an open issue in many ways, but especially how they form. And the community, with a lot of money from NASA, built the James Webb Space Telescope in the hopes of actually seeing this happen at high redshift, right? So
Yes.
we observe these things going on now at high redshift, and so the
Very nice.
paper is about testing the hypotheses. And so I do want to make a meta comment about the importance of the scientific method, right?
Okay.
So what really matters is what we predict in advance of the observation, right?
Yes.
We are very skilled as theorists at explaining things after we know what it is we want, what we need to explain.
Of course.
And often that's the way it has to be, but really
Post-diction. Post-diction, yeah.
yeah, it's really the a priori predictions that matter. So
Hmm.
what we have to do. And so to make a meta comment, I mean, the way I got involved in this line of research goes back to those low surface brightness galaxies and their
Hmm.
kinematics. And I had made a prediction myself for how they should behave.
Okay.
Uh, One of which was that these would be offset from the Tully-Fisher relation.
Okay.
Um, that did not come true. I was
Hmm.
very disappointed, tried to wiggle my way out of it, basically couldn't. And so I went looking around at the time to see who might have gotten it right. And the answer was nobody, nobody, nobody. Oh, this funny guy, Milgram. And so
Yeah, yeah.
I was really shocked that this had happened. So I went back and read his original papers,
Hmm.
and
Yep.
there's an entire section where he says, low surface brightness galaxies will provide particularly strong tests.
Okay.
Uh, because in his theory, there's an acceleration scale. The
Yes.
lower the surface density, the lower the accelerations.
Yes.
And so, at the time, these were new data. And I thought, my first thought was, great, I now have the data to falsify this stupid theory.
Okay. Good.
That was the attitude I brought to it.
Uh,
And in fact, I set the project aside for several months while I finished up something else. And when I came back to it, it's like, okay, let's go through what he predicts. And it was just like, check, 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 check.
cool.
So so what am I supposed to say? He had predicted everything I was seeing well in advance. So that goes back to my first meta comment that,
Right.
the scientific method is, teaching us to respect that predictive success and to take it seriously. So I did, and I've been trying to test this theory ever since, and this is one of the ways.
Cool.
So
Very cool.
a few years after that experience, I was thinking about how galaxies might form in MOND. Um, and I got this paper to review from Bob Sanders.
Okay.
Um, and I was very disappointed because he had totally scooped me. I was working on exactly doing that at the time. And he spelled out how he thought it would happen in MOND. So let me
Okay.
first describe how galaxies form in MOND. And
Okay.
conceptually, the easiest thing to think is about, the early universe. The conventional omega matter goes towards unity, right? Everything
Yes.
in the
Yes.
matter-dominated regime is very close to omega matter equals 1. There are
Yes.
these slight differences that we observe in the temperature fluctuations of the microwave background. And so those positive density fluctuations you can think of as a little closed omega greater than 1 universe, if you
Yeah.
like.
Okay. Okay.
And then
Sure.
that'll take a little cycloidal evolution and recollapse and form a galaxy, right?
Yep.
That's the conceptually simplest way to think about it. Of course, the reality is more complicated, and we'll come back to that, but just have that sample picture. You have a region, it expands, it stops expanding and recollapses under its own gravity.
Yes.
So you have
I'm
to redo that in MOND. Now, one of the well-known problems of MOND is that it's not a relativistic theory, and we don't actually know what cosmology does
yes.
in MOND.
Yes.
But we know the universe is expanding, and we know that
Oh, yeah.
MOND often provides a good description of the dynamics of things within the universe.
Okay.
So the idea is, okay, same thing. We think of a isolated sphere. What is its dynamics in MOND? You can write down that equation, which is one of the equations we'll get to.
Okay.
And you have to solve that numerically. It's not as pretty as right in the standard Newtonian case. It's just a sphere. You can solve that analytically. It's very easily.
Cool.
But what you find is that any sphere will eventually recollapse, absent something like dark energy that fights that
We'll hold it up. Yeah.
recollapse. And so Bob Sanders's hypothesis, which was built on basically a decade before his work, Jim Felton had tried to do this Newtonian cosmology trick for all of Mond.
Mm-hmm.
Found it doesn't work. But what Bob and I independently realized, and why we were working on it at the time, was that um, what Felton had really solved was what we used to call the top hat overdensity problem.
Ah, yes.
Just
Okay.
what happens to a sphere within the background cosmology.
Mm-hmm.
And in particular, you can use that to calculate the time scale of collapse. How long does a particular sphere of a given mass take to expand, decouple, and recollapse,
Okay.
and make a galaxy, something like that.
Mm-hmm.
Um, so Bob did all that. I did it after him, got basically the same answer. Other people have done it since, and there's a variety of answers, some of which um, the very large scale structure is still an open question, but consistently what everybody found was that if you have this nonlinear force law that is Mond operating in the universe, then it's very hard to avoid some structure forming very rapidly.
Mm-hmm.
That is, the time scale for this expansion and recollapse is
Faster.
fast. It's very short. Hence the title Accelerated Structure Formation.
Yep.
Um, and so if you want to go to figure two,
Yeah, let's slide
that
in. Go to
is
figure two. Let's slide in.
what Bob predicted. And this is basically a reproduction of one of his figures
Oh,
with
yes.
logarithmic scale. So I can
Sanders
cram
88.
in all these different mass scales. But
Mhm.
basically, you can see here graphically what I was just saying, that a sphere of a given mass expands, decouples, recontracts. In linear space, these are symmetric. They go up, they can fall back down. In log space, it looks funny like this. But I use the log space so we can show the different mass scales.
Mm-hmm. All good.
Globular clusters are small, they collapse very quickly, and then you go up the scale. So this is all the predictions that were made in the previous century, basically, by
Mm-hmm.
Sanders.
Cool.
Um, and so globular clusters, as he argued at the time, was basically the right scale to collapse first. So it makes sense that they would be the oldest things. And then larger scales collapse, and we're going to talk mostly about galaxies and maybe some about clusters towards the end. But basically, that massive galaxies, something like 10 to the 11 solar masses, and we're talking just about the baryonic mass, right? The stars and the gas. There's
Yeah, yeah, yeah,
dark
yeah.
matter to help out here.
Mm-hmm. Right, right.
That expands and contracts in about 500,000,000 years.
Okay.
So that's what sets the time scale. Okay, so that's the prediction of Mond, as I say, first predicted by Sanders and reproduced by me and by others. Let's go up to
Mm-hmm.
figure one now, because what we want to compare
Yeah.
that to is, of course, the standard lambda
Burger
CDM
tree.
cosmological model, and there's been an enormous amount of work done
Many,
on this.
many.
Yeah, so it's hard to summarize. And
Yeah.
so
Good,
this
good,
is an
good, good.
attempt to do that. And I have adopted for this illustration a figure generated from the TNG 50 Illustris simulation.
Uh-huh.
Um, Lots and lots of work just done on that simulation. And of course, there are
Oh,
many
indeed.
other simulations, but they all show something that's qualitatively similar. And that is that the simple picture that I described of one sphere going up, recollapsing, falling back down, is inadequate because, of course, you have little things that are all doing this within bigger structures, within yet bigger structures.
Right.
Something we used to call the halo and halo problem.
Mm-hmm.
And you can see that graphically on the left panel. That's a
Burger tree.
single, as they call it in the simulation, subhalo. That is one galactic object.
Mm-hmm.
Uh, and the size of the circle is proportional to the halo mass.
Mm.
The
Okay.
color has to do with the star formation rate. You can see the color bar on the side. And of
Hmm.
course, the critical thing in the hierarchical structure formation paradigm is that those all those little things merge to form a
Yes.
big thing. So
Mhm.
there are two fundamental processes going on to get to the stellar mass that we observe. One is just in situ star formation in the largest progenitor. So the
Okay.
closest thing we can think of as being the galaxy. Of course, there are many, many, many progenitors. It's just there's one we kind of say is the galaxy, which is not quite the right way to say it because there
Yeah,
are
but I
so
get
many
it.
mergers. But you can see the largest progenitor on the side, how it grows up. And so one aspect of the growth of stellar mass that we can actually observe is that in situ star formation in that subhalo. But then it has all these other things merging in all the time. So the second object is that growth by mass. And that's fundamental to hierarchical formation.
Indeed.
Now,
Cool.
as Bob Sanders discussed in his original paper, of course, the same thing should happen in MOND. It's not fair just to think of a single sphere. All these small things are going on into big things. And so it's a similar picture, but the time scale is compressed for the reasons I already described. It all happens very fast. So
Yes.
that large thing, all that merging is done in the first billion years or so.
Yeah. Hmm.
Whereas here you can see the
Yep.
time scale is different. So this I picked to represent a typical early type galaxy, something we would call an elliptical nowadays, which is red and dead, right? The star formation is basically quenched around a redshift of 1,
Yes.
and it's not doing anything in the way of growth since that time. And you can find all sorts of examples of this, but generically they look the same. Sometimes the merging continues until late times, and sometimes they keep forming stars, but this
Yep.
merging is generically what we see.
Hmm.
And so, of course, what the simulations tell us is how the mass assembles. That's what you see in the merger tree. And
Hmm.
what is extremely well predicted by the simulations is how the dark mass assembles into those halos.
Yes.
Um, the tricky part is what we observe, right? How do you relate that to the stars that we can
It's the
see?
simulation. Yes.
And so they have some prescription for star formation rate. Different simulations have different prescriptions. So you get slight variations on that. But
And
again, the time scale to make a lot of mass to assemble into a single island universe, to use the old-timey expression for a galaxy, is long, right? There's a lot of this merging. It's still going on till fairly late times.
hmm.
And so in the right panel, you see the growth of stellar mass in what you would identify as a single object looking back in time. That is the growth of the single progenitor.
Hmm.
So the dashed line is the medium growth rate for galaxies of that final stellar mass in Illustris.
I'm with you.
And the sort of the width of the band illustrates the plus or minus. I think it's 1 sigma band, 16 to 84th percentile.
Okay.
Um, and then that solid line is the particular object that is illustrated there.
Okay.
So you can see it's kind of zigzagging around the median, but it's fairly
And
typical.
there. Okay. Good. How about this purple line? What's monolithic mean?
So that I've labeled monolithic. So now we have to step back even further in our guesses about how galaxies form,
Okay.
right?
Then
Before we had the hierarchical paradigm, we had the monolithic galaxy paradigm,
Pagan.
which was pretty much what I laid out at the beginning. You imagine a big ball of gas, how long does that collapse and form? And the answer was a long time,
Right.
but we didn't really know the details.
Okay.
But what we did know from way back when was that there are these big elliptical galaxies in the local universe, and they appear to be made of old stars.
Hmm.
And so people came up with model star formation histories, and I think that's like equation 1 or something like that, if you want to show
Okay.
that.
Yeah, let's take a look at
Um,
those. This is APJ. We're not scared of equations.
I
Let's
think
take.
it appears after figure
There we
1,
go.
but
Exponentially declining star formation history.
yeah, there we
Hmm.
go. So So equation one, right? Just the star formation rate. And
Mhm.
that's what that blue line shows. It shows the integration of that, which is
Ah,
equation
okay.
three.
Okay.
So that, yeah, that purplish line is traditional monolithic elliptical galaxy model. It
Yep.
forms, however, makes a lot of stars fast, and then that star formation is quenched pretty early, and they just evolve since that time.
Cool.
And so that's the comparison. And if you're curious about the details, you can allow for different star formation timescales and whatnot. Uh, but the model that's illustrated in figure one there has an e-folding time of 1 gigayear.
Okay.
So
Hmm.
makes most of its stars very quickly, and
Okay.
reaches a final mass that was
Ah,
chosen to
there it is.
match L
Got it.
star for elliptical galaxies.
Okay. Cool.
And I pick out that particular model one because it's what we used to think was plausible for elliptical galaxies. Two, it's also like your boilerplate first guess for any stellar population model.
Okay.
And it turns out to be pretty good.
Cool.
So,
Good.
spoiler, if we want to make this work out in Lambda CDM,
Okay.
we have to morph that predicted dashed line into that purple line. That purple line is what
Okay.
the data
Okay.
look like. Now, not necessarily everything, but there is, and this is just an empirical statement, there appears to be a population of galaxies that formed early and became massive quickly.
Little red dots.
In exactly in the traditional picture of elliptical galaxy formation.
Hmm. Hmm.
And so we need some galaxies that do that. And you can see just from where the band is that that's an outlier to the
Yep.
way that the pre-existing simulations predicted things. And this is why everybody was so surprised when JWST saw all these bright high redshift
Red dots.
galaxies.
Yep.
They shouldn't be there yet. What we should see is that bottom row labeled Z of 10, where everything is in these little bitty pieces and not
Tiny
already
pieces.
one
Yes.
big.
Yes. Even here. Yep. Very.
So yeah,
I'm with you.
so that monolithic model, it turns out, is a pretty good proxy for the accelerated structure formation that is predicted in MONT.
Cool. Okay.
If you go back and read the Sanders's paper way back in 1998, he explicitly said in the abstract that L-star mass galaxies would form by redshift 10.
That's the
That's
prediction.
that was the prediction, and that seems to be what we are seeing.
Just to
And
loop back to
that's
your
really
scientist.
not what we expect in Lambda CDM. And it's not just because of how the star formation works. It's because of the more fundamental prediction that the mass should take a long time to assemble hierarchically.
Right. You got to
Right.
build it up.
So the outlet is then to change the star formation history to pile it
To
all
pile it
into
up.
the
Yeah. Yeah.
largest progenitor.
Yep.
But
Yep.
that's not really a natural thing to do. So um, let's scroll to those equations a little more because
Okay.
that monolithic case is just an example.
Mm-hmm.
One can, of course, vary the parameters and have all sorts of
Oh, sure.
results, and people do that, right? There's an enormous literature
There's a
on
whole
doing all
industry on
sorts.
this.
Yeah, exactly. So I did generalize this in equations 4 and 5. So
Yes.
equation one is the traditional exponential star formation rate. If you think about it, it's kind of silly because it's just nothing, nothing, boom, it's all full on, and then it decays away.
Right.
So equation four generalizes that to give a linear ramp up,
Then,
and then it quenches
yes.
exponentially.
Yes.
Okay.
Mm-hmm.
So
I'm with
it's
you.
yeah, so it's basically the same, just with a finite ramp up time. And that ramp up time was sort of motivated by Dan Kelson's work. He and his collaborators had said, well, okay, if we're accreting gas onto something, how rapidly, just statistically, from stochastic star formation will that build up? And basically the answer is that the star formation rate increases linearly until something quenches it.
Mm-hmm. Yay, damn.
So that gives equation 4, which integrates to the stellar mass, the observable, in equation 5. Um,
Yes. Oh,
and
yeah.
I must admit, I like this form because you integrate that form. It's the same as the integral of an exponential disk, which is what I
Oh, yeah, yeah,
cut
yeah,
my teeth
yeah,
doing.
yeah, yeah, yeah.
Um,
Right, right, right. Uh-huh.
but so that U variable is the time scale. You
Yeah.
can pick different formation times. You can pick different quenching times. That gives you the flexibility to do just about anything. So
Mm-hmm.
I have in this paper restricted myself to quenching times equal to that formation time for the most part, just
Fair
so
enough.
that it is not too wild. But that's just a slight generalization of the exponential model, which is, like I
Mm-hmm.
said, sort of what we thought was true for ellipticals all along.
Right.
Now, this brings me to a slight aside on downsizing. Because of that hierarchical mass accumulation, and ellipticals being the most massive local galaxies, you would kind of think they formed last. That is, they
You
take the
might think
longest
that. Yes.
to build up, and if there is a lot of star formation going on associated with each merger, they should also look the youngest. And that's the opposite of what we see, of course.
Yes.
And so there was some, discussion of this some years back. But ultimately, we realized that what we observed are the stars are old. So it's
Yes.
okay if the stars all form in those little pieces early on and then assemble through a series of dry mergers, right?
Yes.
There's not a lot of star formation necessarily associated with
Right.
that. So the stars can be old and they only assemble late. And that's the great thing about JWST is now we're seeing those things early on,
Right.
and we're not seeing lots of little things that have yet to assemble when they should be in little pieces. We're seeing big things that are already assembled.
Correct.
And that's a hard thing to get out of. And in fact, most of the paper is about lambda CDM and saying, well, what did we predict? How can we get out of this?
Right. Right.
And relatively little about Mond, which is like, well, that's what Bob predicted, and that's what we see. So that's so let's go on to figure 3.
Okay. I'm with you.
And
Um,
so this comes more or less directly from Jay Frank's thesis.
governing equations
And
for
so yeah, equation 6 is
yeah.
what Mond
Gotta cover it.
predicts. So
Yep. For
it's
the
a numerical solution
or
of
not.
that, which appears
Uh-huh.
in figure 2.
Yep.
Uh, and that's what sets the time scale.
Cool. I'm with you. Let's go down to figure 3 and redshift dependence. There we go.
So this is the characteristic apparent magnitude, in this case at 4.5 microns from
Hmm.
Spitzer,
Okay.
of galaxies and clusters of galaxies as a
Okay.
function of redshift.
Yes.
So what J. Frank was interested in was identifying protoclusters. What are objects that will become clusters at later times?
Okay.
And so he did a lot of searching for those things.
Okay.
And that's the sort of lighter blue points that he came up with. There are data from other people who had done similar things as labeled there. Um, and if you go back and look at Jay's papers, you'll see something similar to this also in other filters and so forth,
Mm.
and lots of different star formation history models.
Okay.
We
Sure.
considered all sorts of things. I've cleaned those out in this case because the one that works is that simple exponential star formation rate model. So that
Okay.
tau of 1 exponential that formed at redshift of 10.
Mm-hmm.
And I asked Jay to build that when he first started building star formation models. Because, of
Okay.
course, there are lots of freedom. You have to make sure you're doing the right thing. And I'm like, here's a boilerplate, generic exponential model. Let's be sure you're comfortable doing that
Yeah.
before we do some more
Yeah.
complicated
Yeah.
things.
Yeah. Yeah.
So, at the time we did this nearly a decade ago, it was just like it was just an example. It was an exercise. We didn't expect it to really represent things because and it's worth remembering this because we've gotten spoiled already with JWST, but a formation time redshift of 10. That was just crazy talk
Yep.
uh,
Yes.
more than 5 years ago. Um, and so we picked that number just not because of Bob's. I mean, I remembered Bob's result, but I was not thinking about that. I was just thinking that is a crazy high redshift,
And it's a round number.
arbitrary early to as far as we were concerned. It was starting at t equals 0 practically.
Right. I'm with you.
So that was just a boilerplate thing, and it turns out it works better than everything else we tried. Lots and lots of other models. And so let me go back a little and say a little more about the data.
Okay.
Each point represents a single cluster or protocluster. So
Okay.
it's not one galaxy. Each point represents all the galaxies in that cluster. So
Okay.
it's a Schechter fit to dozens and sometimes even hundreds of individual galaxies.
Yes.
So those are lots and lots of points, and they're all spectroscopic redshifts.
Ah,
Um,
good.
I,
Okay.
in, I
Right.
insisted that Jay
Yes.
find spectroscopic redshifts for
Yes.
everything that was
Good.
done. So
Cool.
one of the things you can see in his thesis papers are sharp spikes in the number as a function of redshift, and that was one of the ways he identified
Got it.
these protoclusters.
Cool. Very
Um,
nice.
so you can see that the evolution at low redshift is well matched by this exponential model.
Mm-hmm.
That's a non-trivial result right there. But it also goes back more or less as the scatter of the data. And of course, as you get above redshift 2, there's not a lot of cosmic time there. So
Yeah.
you expect some scatter, and that's sort of what we see. But the exponential model does a really good job of capturing the general trend of the data.
Indeed.
So, like I say, this was part of Jay's thesis. You can see that paper cited in 2017. Um, One piece of his thesis that had not made it into the literature were those open squares. So, what did lambda CDM predict at that time? And that was the orange line, which came from the Munich galaxy formation model, which was basically based on the Millennium simulation
Millennium. Yeah, I was going to say. Okay.
with
Mhm.
some prescription for star formation.
Yeah, Springer. Hmm.
And what he was able to do, those authors shared a look back cone.
Okay.
So a lot of these simulations, there's a lot of data, so they tend to spit out, here's redshift 10, here's redshift 5, here's redshift 3, da da da.
Yeah.
Just get slices, right?
Slices. Yeah,
So
yeah.
it's actually an important and big challenge to make a look back cone. Okay, you're an observer in the simulation. If you look back continuously through the universe, what would you see?
They got to get through all those slices. Hmm.
Exactly. So this was a continuous cone looking all the way back. And what Jay did was apply the same algorithm he had developed to apply to data.
Hmm.
That's how he was identifying clusters or things close on the sky. Are they at the same redshift, essentially?
Hmm.
Um, Apply that to the look back cone.
Okay.
So those open squares are
Yes.
what the same algorithm that he applied
Okay.
to the data
Okay.
find when looking at the Millennium simulation.
Hmm.
And the orange line is what the simulation actually says, because you know that from the
Hmm.
simulation directly.
Hmm.
And so
Little
the
gap there.
bottom line of this figure is that if the universe had looked as predicted by those simulations, we
Mhm.
would see it, right? We could tell the difference.
Oh, yeah.
And so we don't. So that was before JWST, there were already indications that galaxies were too big too soon.
Hmm.
And in fact, there was a paper by Steinhardt et al. Around
Yeah.
the same time, 2016, I think,
Hmm.
that basically called it the impossibly early galaxy problem.
Yes.
You should not have galaxies this massive. And it's not because of the star formation history, it's because of that hierarchical mass assembly, right?
Yes.
That's the thing that we would like to test because that's what the theory fundamentally predicts. But we have to have some prescription for star formation, so that's where we can always play around.
Yes. I'm with you.
Okay,
Hmm.
so this is what we knew going in, and in fact, I had written this paper in 2001. So when JWST was launched, I had a little blog post reminding everybody that Sanders had predicted this, and so this is what we should expect to see. And I thought, okay, well, I should write the actual science paper, and I knew this much, so I had written this much. And then I was just going to quickly insert what JWST first found and publish
Right.
it 3 years ago.
Hmm.
Well, you notice it's been three
Well,
years.
well,
Um, so there's a lot more.
something
And so
happened.
what happened, and this is an important part of the story, is
Yeah,
that, of
yeah.
course, when JWST first started reporting results, it was, oh, there are these galaxies that are too bright, too early. Everybody was all concerned. And at first I like, great, we'll plug that in. And I'm like, do I
Mm,
believe that? Um, and so pretty soon after that, people started objecting to the photometric redshifts.
yes.
And that was always a concern. That's why I insisted J use only
Spectroscopic.
spectroscopic redshifts.
Right.
And you really do get a much finer redshift resolution. If you redo J's work with photometric redshifts, you cannot see the clusters because it's not accurate enough to pick out the spikes in redshift space.
Right. Okay. Hmm.
Um,
Hmm.
and then it turned out, of course, that the first results were relying on the calibration of JWST that had been done on the ground, and they did
Yes.
not yet have the on-sky calibration, so that changed all the results. So I
Mm.
was right not to publish right away,
Good for
right?
you. Good for you.
Yeah, so it's like you never get credit for what you don't do, right? But sometimes you should. And so I refrained and wanted to let that sort out. But
Totally.
of
Yep.
course, it took a while for that to happen. And then there's an enormous amount of interest in this. So there are lots of really talented people writing all these great papers on JWST data, which I felt obliged to keep track of. So it's just that to keep our, for 3 years, basically trying to keep up. And of course,
Now
this
there's a
was
merger tree for you.
yeah, it was a fire hose. It was a proverbial drinking from the fire hose, and it wasn't even so much what I was doing. It was just trying to keep up with the
With the
literature.
community. Yeah, yeah. Yeah. It was
Um,
exploding there for a bit. Hmm.
in the end, I think that was worthwhile because we now have a lot of spectroscopic redshifts.
Yes.
I
Yes.
still hope that improves, but it corroborates a lot of what we were saying.
Cool.
So let's see. Let's
Beautiful.
move on to figure 4.
Beautiful. Okay.
Okay, so remember figure 3, that purple line, that's what
Okay.
we see. So that apparent magnitude is what you see for these for L star of these different clusters. Now let's turn that into a stellar mass, and that's what I
Ah,
do in
okay.
figure
Big
4.
four, turning that into mass. There we go.
Okay, so that purple line's again the same line, that simple exponential model that Jay
Yes.
made,
Yes.
forming at Z of 10, 1
Mm-hmm.
gigayear decay time.
Mm-hmm.
But now instead of the apparent magnitude, it's the stellar mass.
Here we go. Let's turn
And so I've called that M star star, right? It's the stellar mass, M star, but it
oh, there we go.
corresponds to
Yeah,
the
yeah.
mass of an L star galaxy. So
I'm with you. Yes, I understand.
it's, that was one of the more contentious things among the co-authors is what do we actually call this? This is a terrible thing. No, it's great.
Well, you don't often
So
see
that's
superscripts and
what I went
subscripts
with.
today. Yeah.
And all the data on this plot still predate the JWST. So there's the same data that you saw before. And of course, because of the sort of inverse relation between redshift and time, now I'm plotting linear time. And
Mm-hmm.
that emphasizes that most of cosmic time is after Z of 1, right? So
Yes.
that gets you back to, just 6 gigayears or so after the beginning.
Yep.
And where you saw all that evolution in luminosity, apparent magnitude space,
Yes.
there's none in stellar mass. These galaxies are quenched. That's just stellar evolution. And so that mass is pretty flat all the way back to redshift 2, and then you see the scatter kick in. But
Yes.
again, clearly they follow along that. And of course, there was work done after Jay's work, but before JWST, those light blue points are one of these works from Stefanon. And I picked those out. There are a number of other really excellent references. I picked those particular ones because they're the most conservative in the sense of having the lowest mass estimates at that redshift.
Okay.
So if I plot all those other points, then it becomes a chaos of everything jammed into that first giga-year. But there are a lot of points that are already up much higher than that
Okay.
from that period.
Cool.
Of
Okay.
course, you start to have it to rely more on photometric redshifts at that period. Even so, that is clearly different from what the simulations are predicting. So
Right. Good.
the
Lustrous
dotted
fire.
line is that same model that was in the previous figure. The dashed
Yes.
line is
Yes.
Illustrious, which is, of course, the follow-on to Millennium. And
Millennium.
so they've clearly picked the same star formation prescription. So you can
Mm-hmm.
see the same median growth of stellar mass that reaches that approximate final mass.
Fire.
And then for comparison, I've worked in the fire simulation, which is a bit more, forms stars a bit quicker, has more feedback. And
Does.
so it does ramp up faster, but it's still nowhere near the data.
Right. We're still
And I
well.
attribute that to the difference in the hierarchical assembly, right?
Okay.
They both take time to put the mass together. So simply making the stars faster isn't
Who's
really
going to do
what's
anything?
happening. It's that the mass isn't yet assembled
Yes.
in theory, but in practice, it appears to be.
Appears to be.
Okay.
Okay. I'm with you.
All right. So, so that's in some sense basically just the same figure as the previous one, but now in stellar mass and also showing other models. And you can plot lots and lots of simulations. It just gets crazy bunch of lines there. So I've refrained from showing every single thing, but this
That's
is
fine.
generically what simulations predicted would happen before they saw the data.
Yep.
And there's a really good reason for that. I mean, the simulations are great. I think they're doing the right thing. It's, the underlying assumption of that hierarchical assembly that's the
Yes.
problem, right?
Okay.
And so that's why those lines are falling short at high redshift.
Cool.
Um,
I'm with you.
see if I can remember what I said. Now, what you'd really like is the stellar mass function, and I had written a short paper about this before that, so I don't, plagiarize myself and reproduce it here.
Yay.
But there is a clear excess in the data you're looking at there over the predicted stellar mass functions for massive galaxies.
Yes.
Now, if you go to JWST data, which is figure 5,
Moving to the
you're now looking at the UV luminosity function. The section header goes by. And so, up until now, I've basically just been talking about what we knew going in, and now here's what we learned from JWST.
okay.
And so this is now the absolute magnitude as a function. The number, these are the ultraviolet luminosity function. Now,
Yes.
again, I'm old enough to remember we built JWST so we would see high redshift galaxy formation in optical bands,
Okay.
right? It's sensitive far enough into the infrared that we should be looking at sensible bands at sensible redshifts, like merely a redshift of 5, right?
Okay.
And now we see all these things at a redshift 10 and above, so we have to push ourselves back to UV.
Yes.
Which is a challenge, of course, because the UV light is a terrible tracer of stellar mass, which may or may
Hmm.
not be a good tracer of the dark mass, which is what we really want to test.
That's what
Okay,
we
so
got.
with that caveat, we do what we can.
Right.
And so the UV luminosity function is shown there, binned by redshift. So at redshift 9 are the darkest blue points. Then redshift 11 is green, and
Hmm.
orange and red for redshifts 12 and 14.
Okay.
That particular UV luminosity function came from Donnan et al. There are other evaluations, some that came before, some that came after I had written, so that's what I had, and that may continue to evolve as we get more data, but that's what I had to work with when I made that.
Okay.
Um, the prediction comes from an analysis simulations by Young et al.
Okay.
2023, and so that's what those lines are.
That's lambda
Um,
CDM.
and that was an already, and I want to praise Young et al. As well, because in a series of paper preceding this, including papers that predated JWST, they predicted what they would see.
Good.
And so, um, they had figures like this in those papers. In the 2023 paper, they were like, well, if we look at higher resolution simulations, then we get more things.
Mm,
And
yeah,
so the
sure.
normalization slid up, and that'll come up in the next figure. But
Okay.
still, what you see clearly as a prediction in those lines is exactly that strong evolution
Yes.
of the predicted luminosity function.
Yes.
And that happens because that's when things are assembling. You have all those little parts that are coming
Oh, yeah.
together, and nothing big has yet formed at those higher redshifts. And you can see the jagged lines at redshift 12 and 14,
Right.
basically because even though they have a high resolution and yet big box simulation, you're just running out of objects. There
Right.
just are very few things that redshift 14, you say, okay, that's formed and has this
Right.
mass that gives you this luminosity. Um,
A little more
and then in
scattered.
the right panel to sort of give you some normalization, I've basically scaled the data to the prediction at each
Mhm.
redshift, and you can see it's high
Mhm.
everywhere, not
But
just
one.
um,
Mhm.
massive galaxies. Now, the obvious cure for that is to crank up the UV photon production per unit mass.
Okay.
And we're really good at doing things like that. It's
Mhm.
worth thinking about at this point some of the ways out that we might consider how to fix that.
Okay.
And remember, figure two there, I had prefaced this, or figure one really, I had
Figure
prefaced this
three.
by saying you have to turn the predicted star formation history into that monolithic model.
Yeah. Yeah.
That's what you need to explain the data in
Okay.
a nutshell. A
Okay.
great oversimplification.
Sure. Zeroth order, let's say. Okay.
Um, but so you need to put more light per unit mass. That the dark matter assembly is a robust prediction of lambda CDM. So you're not going to get more light out of it if star
Ah,
formation is normal,
right.
right?
Right. Right. Right.
So you need something to goose it. One way that I actually advocate in this paper is what I call super efficient star formation.
Right.
That for whatever reason, star formation at these very high redshifts is much more efficient than it is today,
Okay.
or even at intermediate redshifts. And so you just, in fact, do make a lot more stars out of the available baryons,
Mm-hmm.
right?
Try out earlier too. Mhm.
And you need to turn that way up to do it.
Okay.
I have seen papers where people say, oh, this is a huge problem for lambda CDM because we have to turn half of the baryons into stars, and that's crazy high efficiency.
Right.
And other people say there's no problem for lambda CDM because there are plenty of baryons available. Um, so,
Okay. Hmm.
so yes, but this is, insert Lord of the Rings meme. One does not simply convert all the baryons into stars just like that. And that's sort of what needs to happen. And
Right.
I sketch an idea for that, how that might happen, but it's not what we predicted.
Right.
Um,
Right. This is a post-diction. This is fitting it too. Hmm.
yeah, exactly. And we have a lot of freedom to do that. So
Yeah.
another thing to do is, well, let's not go crazy with that. Let's
Okay.
make
Okay.
more massive stars, not the whole thing, but just that high mass stars
Yeah,
are
okay.
formed more
Okay. Okay. The
efficiently.
stellar IMF. Uh-huh.
Yeah, so a top-heavy IMF, and then
Yeah.
you have
Alpha.
a lot of UV bright sources that live a
Yes.
very short time and
Yes.
conveniently go away later on.
Yes.
So that's a good way to goose the UV light production, which is what this graph is basically about.
Mm-hmm. Yeah,
And you can
okay.
see
That argue that too.
what it needs to do, which is a lot, right? You need a sort of a factor of 10 in UV light production at the highest redshifts.
Yes.
Um,
Yes.
I have on occasion run into claims of variable IMFs in my career, and
Sure.
it has never worked out. And so I am very reluctant to go that route. But if you want to, the thing that kind
Mm,
of
Yeah, okay.
Concerns me even doing that is there seems to be a bit of a fine tuning going on.
Yes. Yeah.
So if you look at the left panel again, the UV luminosity function is barely evolving above redshift 9. All those points, 9, 10, 11 are right on top of
Yeah,
each other, 12's a little lower. And so
fair.
there's very little change in the UV light that's being produced by these things that are evolving rapidly, right? Following the solid lines.
Uh-huh.
So you have to not just invoke a top-heavy IMF, but in this fairly narrow window of cosmic time, just a few 100 million years, you have to tune how much of a top-heavy IMF you always have to keep that UV luminosity density almost constant, even though the underlying mass is evolving like crazy underneath. So
It definitely sounds like tuning.
yeah, so it's not just that you have to tweak the IMF, you have to tweak it just so.
Correct and in the right times, in the right places. Too much, too much.
There are, of course, other things you could do. There could be less dust attenuation, so you're simply seeing it better. You
Okay.
have the same fine-tuning issue, right? You
Right.
have to have the dust do a peekaboo in reverse as you go to higher redshift.
I like that. Peekaboo.
I'm
Okay.
sure there are other things you can do, and probably other things that I wrote about that I don't remember now, because
Sure.
I'm sure our audience has had the experience that you write a paper, you're all into it, you know every detail, and then by the time it's published, you're like, oh yeah, that's old news. It's new news to you, but I went through all these things, and there's no clear solution.
Right.
Um, and it comes down, I think, to what I said. It's not the luminosity evolution that's the problem. I think the simulations do that perfectly well. It's the
Right.
mass assembly.
Correct. Correct. Yep.
So da 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 da. Okay, so let's move on to figure 6 then.
Okay.
And so that was the luminosity function. That's what you really want to know. And I look forward to seeing a lot more of that kind of data from JWST.
Ooh,
So that
we will come back to that point. Okay.
um,
Here we go. Mass estimates.
And so this was when I said I was just going to do a short paper 3 years ago. This was going to
Yeah.
be the add-on figure from JWST.
Okay.
So it's just the stellar mass now of individual galaxies, not
Yes.
entire clusters, right?
Yes.
As a function of redshift. And you can now see we're looking at very high redshift, 6 and above here.
16. Yikes.
And so some of those were the first points. In fact, the open squares, I think, were from Labe et al. Or maybe
Yes.
Naidu et al. They
Yeah.
were some of the first to report,
Mm-hmm.
and those were some of the numbers that changed.
Okay.
So that's what I refrained from publishing because I wasn't sure I trusted them. Since that time, the calibrations have
Well,
been
yeah.
settled. Everything has been reanalyzed, and so that population of open squares at the top left, all those data changed, every single galaxy, and yet the basic conclusion has not. So they are a bit lower mass, they're at a bit lower redshift, but they're still too much. And
Okay.
now you can see there are a lot of course, other people have done this as well. So every color is some different study.
Yes.
Um, and there are lots and lots of people who've just been finding lots and lots of galaxies at high redshift. Now,
Indeed.
I don't think we should believe every single one, but I don't think we can have the option of disbelieving all of them, right? And so this has become, and one of the reasons it was worth waiting is that there are now a number of spectroscopic redshifts. So
Correct.
the
Yep.
colored points were what I put on early. They were all photometric redshifts. The black points all have spectroscopic
Got it.
redshifts. And
Cool.
there the different symbol types are again from different groups working on this.
We got some shading going on here. Dark shades of gray, light shades of gray. What are those?
So those are the theory.
Mm,
So the dark
of course.
shade is the hard limit of there aren't enough baryons to make the stars.
Okay. Yeah, that
That
is
is to say, you have small halos that are assembling, they only bring their cosmic fraction of baryons along with them.
right.
And so if you turned
Limit.
100% of those baryons into stars
Yep.
with a normal IMF,
Yep.
um, just like that, then they would be at the edge of that dark region.
Mm-hmm.
So anything that is for real, for sure, above that is just death, right? It can't happen in
Right.
Lambda.
Understood.
And, we don't see anything. There are not a whole lot of things up there. There are a few things that challenge the edge, but there are
Challenge
bars
the
are
edge.
consistent with
It
being on the
challenges
other
the
side.
edge, but there's not stuff like up here, right?
Exactly. So, in some sense that could be taken as encouragement.
Yeah.
On the other hand, you still have to make all the stars all at once right away. And
In those.
that's not too
That
reasonable.
doesn't sound very plausible. How about the gray, lighter gray?
So the lighter gray region is just where we expected galaxies not to be. So the
Okay.
lines demarcate what the predictions, again, going in.
Mm-hmm.
So especially
Mm-hmm.
the dashed blue lines, the lower edge of the gray region.
Yes.
Those were the predictions and different lines for different simulations, but they all more or less agree. That was the most massive galaxy that they would see,
Okay.
period. And
Okay.
that's as big as it gets. So there
Okay.
shouldn't be anything to the right and above that line. And so that light
I'm with
gray
you.
region is
I'm
things
with you.
that
Okay.
really should not exist.
Right.
It's not that they cannot exist, but they really, really shouldn't exist.
Sure is well populated, isn't it?
Yeah, so there are plenty of things there, and now a number of things with
Good.
spectroscopic redshifts. So I don't think we can just say, oh, well, the photometric redshifts are wrong.
Mm,
A few of them have famously turned out to be wrong, and that's sort of what you expect playing
science.
this game. I think a number of them have turned out to be right and spectroscopically confirmed. So
Right.
it's a mix, but there's enough things there. I don't think we can simply dismiss
You
it.
just, yeah, throw it away. Cool.
Now, like I say, we can always turn the knobs. And so the blue dotted line, I had mentioned that Young et al. Had made a good prediction, but then they
Mm-hmm.
found more things in the higher resolution simulation. So that blue dotted line is their adjusted prediction, whereas the dashed line was their original prediction.
Okay.
So that shifts up the
Got it.
normalization by a factor of two, 2.5 or so.
Okay. Mm-hmm. Yeah, log scale.
So, that helps, but it doesn't really
Solve it.
change the basic picture, really.
Right.
And then the red line is my own assessment from TNG 300.
Okay.
And basically, I just went through that simulation and asked what is the very, very biggest thing in that entire simulation.
Mm-hmm.
And I made no attempt to normalize for the area surveyed. So that really is just the biggest thing
Okay.
that forms. And so
Okay.
I think of that as a pretty hard upper limit because if you make the renormalization, then it just moves back down to where the other lines are to begin with.
Correct. Yes, I'm with you. Uh-huh.
So things really shouldn't be in that light gray region, and yet they are.
They
So
are.
that was going to be the four-figure paper 3 years ago. But I didn't
Now it's gone
believe
out
the
to
data. I
11.
didn't believe the data yet, and I was wrong, right not to believe it yet. But yet those data have not changed enough to change the basic answer, and
Okay.
that's what we see now.
Cool.
Um, so
Good summary.
an important thing now is how those things evolve. So, right, we saw in figures 3 and 4 how the
Four.
stellar mass builds up over time.
Yes.
We see here what the expectation from the simulations for individual galaxies are. And we've talked about, maybe there's a top high of the IMF or it is crazy high efficiency star formation.
Formation.
Can we do anything about how individual galaxies form and evolve? Because we're now seeing slices in redshift space, right? So we can actually,
No.
it's like an HR diagram. You only get a snapshot now. But
Okay.
can you compare galaxies at redshift with 3, with 4, with higher redshift?
We want
And of
to.
course, you can never say this galaxy had exactly that evolution, but you can ask for consistency's sake. So looking at this figure, let's see, it's 10 to the 10 solar masses that
Uh-huh.
it maxes out at about redshift 7.
Thereabouts.
Um, t- t-
Uh-huh.
t- t- um,
Yeah.
yeah, so it's on that plot. But um, basically, we're going to now shift and let's look at figure 7.
Okay.
So those were what's going on at high redshift. Now let's look at sort of intermediate redshift, which is still early in cosmic thought.
Or did I miss one?
Yeah,
No, that's 6 and this is
that's
7.
6, and here's, I
7.
hope,
Okay.
7. Yes.
Okay.
So the
Yeah, we're
redshifts up
lower.
at top,
Mm-hmm.
right? So now we're going as low as redshift 3. And remember, redshift 3 is still pretty early in the universe, right?
Yes. Yeah.
So the cosmic time is at the bottom. So at redshift 10, that's roughly 500 million years after the Big Bang.
Mm-hmm.
And then it shows the next giga year and a half after that.
Yes.
So those red points are all galaxies observed by, I hope I can say this right, Nana Yakara et al.
You did a great job on that. Yes.
Part of Carl Glazebrook's group.
Mm-hmm.
And he's
Yeah, yeah.
been pursuing this for a long time.
Okay.
Um, and so they have spectra and enough spectra to fit stellar population models
Okay. Okay.
and infer what the evolutionary history of these things might have been.
Right.
So the red points are the stellar mass and redshift as observed. So all between redshift 3 and 4, but
Yes.
quite massive, between 10 to the 10 and 10 to the 11 solar masses. And the 10 to the 11 solar masses is a huge number at redshift 0, let alone today.
Right. You got some big ones. Yes.
Yeah. And so
Massive.
these galaxies are all quenched.
Okay.
So they've
Sure.
basically stopped forming stars. And so those orange points are examples of when they infer the quenching to have happened.
Ah, okay.
And they
Uh-huh.
define it to mean when 90% of the stars have formed.
Fair enough.
And so
Okay.
those are the orange points, and I could put them on for all the galaxies, but then it just becomes a complicated mess. So
Right. No, this gets
I've
the point
only shown a
across.
few
Yeah,
examples.
yeah. This gets the point across. Uh-huh. I'm with you.
And then the small green points are
Mhm.
the same thing, but when half the stars have formed. So
Got it.
how long does
50%
it
point.
take
Mm-hmm.
to half the stellar mass?
Mm-hmm.
Now, if you remember from back early, figure 1, I said it takes about half a Hubble time to form half the stars in most of these lambda
Yeah.
simulators.
Mm-hmm.
Takes about 7 gigayears on
Okay.
average to form half of your stars into a final object. Well, here we can see a bunch of things that have reached half of their final stellar, well, the redshift 3 stellar mass already in the first gigayear or gigayear and a
So,
half,
yep.
right?
Yep. These three.
So now those dotted lines are star formation histories from that equation 4 and 5 that
Cool.
I had the linear ramp up and then exponential quitching.
Cool.
And those numbers are
Mm.
just the
Worked out well.
e-folding time and the formation time that it takes to fit those data,
Ah,
taking them
okay. Thank
literally.
you.
Now, of
Mm-hmm.
course, there are big error bars, so you know I wouldn't take this literally, but the point is that these things formed fast and are consistent with just being island universes that are sitting there forming their stars very fast, and that now
Very good.
have stellar populations consistent with being the descendants of things that did that.
Cool.
Um,
Yeah,
so
it's the same shape as
this
what we saw
is
before too. Mm-hmm.
an important constraint, I think, on any weird ideas that we want to have about top-heavy IMFs or super efficient star formation and so forth and
Mm-hmm.
so on. I mean, we can certainly consider those.
Sure.
But the descendants of high redshift galaxies already look like they're just on the path of a normal monolithic model.
Yep.
And so you can't make it too crazy and also respect, without you have to respect this too.
Indeed.
So,
Cool.
it's not just that we see bright things at high redshift that appear to be overly massive, right? It's not just that there's the UV. It's that these things appear to have descendants just a gigayear or two later. That is exactly what you would expect for a stellar population that had formed all its stars normally,
Sure. Yeah.
just done it really fast.
Right. I just assembled a lot quicker. Mm-hmm.
And so the only way to do that in a single object is to assemble them more quickly. And again, hence the title, accelerated star
Accelerated.
formation. Yeah.
Mm-hmm. Very cool.
Um,
Okay.
so Um, let's skip forward to figure 8, more based on their work. So
Let's go to figure eight and what we
they,
got here. Star formation. Yeah. Yeah, okay. Hmm.
So this is the star formation rate. So from their modeling, they put a limit on what the star formation rate at the epoch of observation is. And that's what those red symbols are. And there are a couple that have a measured star formation rate, but most of them are upper limits. And they would fall way off the bottom of this list. They're basically red and dead
Gotcha.
objects.
Gotcha. Yes.
Um, and
Yeah.
those things basically don't happen in the simulations. So the black squares are
Yeah.
galaxies selected to be the same same stellar mass
Mm.
range as the observed ones at the same redshift. Redshift
Factor
3
10.
is um, you get 3 and 4, and 3 is the more conservative choice
Okay.
for this illustration. And you can basically see that they're done. There's a nice star forming main sequence, right? This star formation rate correlates with stellar mass in the way you would
Hmm.
expect.
Hmm.
But that is nowhere near um, where the actual data are.
Yep. Again, a factor
And
10.
so the black points are TNG 50, which is the higher resolution simulation, which I expect is the more appropriate comparison.
Okay.
The open squares are TNG 300, which is a
Okay.
bigger box,
Hmm.
but
Hmm.
lower resolution. So when you have that bigger box to search through, you do see a few things at lower star formation rates
Yes, definitely.
that
Yeah.
really aren't present in the higher resolution simulation. So
Right.
are they there just because we've had a much bigger volume to search,
Yes.
or should they not be there because of resolution issues? Either way, they don't really describe what we see in the data. There
Yeah.
are a
Either way.
lot of massive quenched galaxies there at redshift 3 and 4 that just were not anticipated.
Right.
Um, and again, I think that's because it's the mass assembly that's to blame, not the star formation modes.
Yes.
But all the papers I see trying to address this problem are all about the star formation, because that's the knob we can turn. We can't really do anything about the mass assembly. Um,
Maybe. Okay.
well, maybe, yeah.
Maybe. Okay.
So in Lambda CDM, we think we understand the
Fair
answer.
enough. Fair
Put
enough.
it that way.
Fair enough.
And historically that has been an issue, right? The
Oh, yeah.
observer's experience has been that there has always been more structure in place sooner than was predicted by contemporaneous models. And so, people are very fond of how well Lambda CDM explains large scale structure, but we invented Lambda CDM because standard CDM fell short, right?
Right.
And
Right.
and so we keep pushing it this way. So that is an important constraint, I think. You have to explain these intermediate redshift results, which are still early in the history of the universe.
Yeah.
And what's going on then is obviously related to what's going on just a gig a year before at very high redshift.
Hmm.
So you can come up with a model maybe that explains redshift 10, but are you going to get that right later on?
Right. It's equal.
So for example, um, the highest resolution simulations I know about, Harley Katz, who was an undergraduate student of mine, was involved in Sphinx. And the
Wow.
Sphinx
Okay. Hmm.
simulation seemed to
Yeah.
do a pretty good job of getting the surface density of JWST galaxies right.
Nice. Okay.
Um, but the rate of growth, and that I think is so because they're high resolution, so they see lots of things
Cool.
well.
Yeah.
But that makes it computationally expensive. So they've only evolved it as far as Redshift 9, so
Ah.
far as I've heard. You
Ah.
don't see everything after
Ah.
that.
Okay.
And it looks to me like the slope, the rate of growth is basically parallel to other Lambda CDM simulations. And
Okay.
so if that sustains, and that's an extrapolation, I don't know, but that's the only extrapolation I can make. And if so, they're going to overshoot everything at low redshift.
Okay.
So you need to do all these things all at once.
Okay. Yes.
Now, another constraint is what the actual mass is doing. So far, it's all been
Yes.
the photometry and what we can infer about the stellar populations.
Okay.
So what do we know about the kinematics? And so that's what figure 9 shows.
It moves. It moves.
So there are two plots here. One is the baryonic Tully-Fisher relation,
Uh-huh.
which is the mass of baryons we can see, both stars and gas, as a function of some estimate of their rotation velocity, right?
Yes.
So Tully-Fisher's well established. Everybody knows about that.
Yep.
Um, the black points are data from our own Spark database of low redshift galaxies. So
Okay.
we can see those two very low masses, and so they extend to lower mass and velocity than the high redshift data, which are from Nestor Shahar et al. And I've binned those into three different redshift bins,
Okay.
sort of lowish, intermediate, and high. And high in this case is 2.5, right? So we have
Okay.
not yet pushed this all the way to redshift 10 by any means.
Right. Right.
Um,
Yes.
there are kinematic measurements
Okay.
of some
Okay.
interesting individual galaxies at redshift 5 up that high, and they're consistent with what we're seeing here, but they're just one-offs
Mhm.
so far. You can't make a Tully-Fish relation out of them.
Okay.
But I think by eye, one does not see a whole lot of evolution there, right? That
Right.
relation seems to have been put
In
in place at
place.
early times, and
Yep.
it just sits there.
Yep. Yep.
And, if you look close and squint, you say, okay, maybe there's a little difference here and there. Bear in mind that in order to plot the baryonic mass, we have to do the stellar evolution right. So we have to have a stellar population model. There's a lot of uncertainty in that. On
Indeed.
top of that, to get the baryonic mass, we're often assuming you don't have to do this at low redshift, but at high redshift, we have to
Oh, yeah.
scale somehow to the gas mass.
Certainly.
So there's a lot of assumptions going in there. So I think, basically there's no serious evidence of evolution given all those caveats.
Fair enough.
Um, then on the right plot is something related.
Dark matter.
The fraction of dark matter that you
Yes.
infer, I
Yes.
think it's at the effective radius. I forget the detail. But if
Oh,
you
sorry.
basically measure, okay, what is the dynamical mass at this radius?
Right.
What is the baryonic mass? What is the fraction of dark matter?
Uh-huh.
Now, at low redshift, this has been established for a long time, something Erwin de Block and I discovered in the 90s, that the lower the surface brightness, the higher the dark matter domination. And this is a very systematic thing. It's
Yeah.
it's
Okay.
not with luminosity, it's with surface brightness.
Mm-hmm. Mm-hmm.
And apparent correlation with luminosity just follows because surface brightness and luminosity are themselves correlated.
Cool.
But the tighter correlation is with surface brightness. And so that's what's plotted on the bottom, some estimate of the surface density of baryons. And again, you can see a relation, and the high redshift
Mm-hmm.
galaxies basically scatter around the same place as the low redshift galaxies. And
Red.
you do have to be careful about how you make this measurement, because as you go to the higher surface brightnesses, the baryons are basically accounting for nearly all of the mass at
Love it.
small radii. So very slight changes in your stellar mass estimate can actually scatter you around a lot in there.
Oh, yeah.
And
Okay.
that's why there is so much scatter in this plot. I think the intrinsic, yeah, exactly.
Yeah,
That's
right here. I
the
mean, that's a fairly
characteristic.
big, generous error bar
So,
there.
yeah, so within those errors, again, there's no indication of evolution. So galaxies
Okay.
look like they do now and have for a lot of cosmic time.
Yes.
And that's also consistent with the morphologies people are seeing, right? There have been Chris Conchalici and his collaborators have published papers about, geez, there are spiral galaxies up to redshift 6. They just look like spiral galaxies, and
Exactly. Yeah,
that
Chris.
is
Okay.
not what we had expected
Not at all. Okay.
in Lambda CDM.
Yeah,
So
yeah.
this is a bit of a digression from the
Deeper
rest of the
paradigm.
paper, but I think it's important because it seems to indicate that whatever is going on here involves the mass and
Yes.
not just the photometry,
Uh-huh.
right? So we can make up all sorts of stories about how the stars evolve and, top heavy IMFs, UV light, la, la, la. But, it appears that the mass, as indicated by the kinematics, was already in place,
Already there.
if not at Z of 10, and certainly by Z of 2.5. And there's not a huge chunk of cosmic time in
Mhm.
there.
Figure two.
Um,
Or three.
so yeah, so that brings us to our summary plot, which is the next one.
Okay, let's go
Um,
down and what we, ooh, this is a busy one. Okay.
well, exactly, and this is why I saved it for the last.
Ooh, okay, this one's juicy.
So
Okay.
this basically combines, I think, figure 3 and figure 10 and some, yeah, more data, right? Data kept coming out.
Okay.
So there's data on here that were not in the submitted version because, of course, science rolls on
We'll
as
move forward. Okay, what
um,
are we going
so where to even begin?
to
Let's start with the red dashed lines at
okay.
left.
Okay.
Those are the predictions from Illustris for the
Okay.
stellar mass
Mhm.
growth of the largest progenitor object for things that are 10 to the 10, 10 to the 11, 10 to the 12 solar masses and stars by redshift 0,
Yes, I'm with you. Uh-huh.
right?
Okay.
So your typical elliptical galaxy has a L star mass of 9 times 10 to the 10. So let's call it 10 to the 11, right? So that model is there.
Mm,
And you can see that the red dashed line falls way short of the big points, which are those same cluster points from
yeah.
before, right?
Mm-hmm. Mm-hmm.
Um, and that ramp up of growth, which in this log linear space is approximately linear, that's what the simulations show. And you can tweak the star formation history to move exactly, but basically that slope is what they predict,
Thanks.
and it gets it wrong. So if you imagine using the process, and you're basically just sliding that line way to the right,
Okay.
and in fact, in figure 6, we had that
Yeah, exactly. Yeah.
solid red line. Yeah,
Yeah,
let's go
let's go
back
back
and
to
take a
figure six for a
quick
sec.
peek at that.
Let's just go back to figure six for a sec. Yeah, yeah. Uh-huh.
So that red line, that is the most,
Massive.
massive galaxy that appears in TNG 300,
Okay.
right? And so it runs from 10 to the 11 at Z of 6
Six.
on down to,
10 to the
whatever.
9 at 12.
So let's keep that in mind. 10
Okay.
to the 11 at redshift 6.
Okay, let's go to the money shot here, which was here.
So that's sort of middle of the point, almost where that blue point is. Yeah.
Yes, right about here.
Okay. But the slope of that line is the same as the dashed lines,
Okay.
right? It cuts across like that. So,
Yes.
that is the most maximum you can be. And there's still lots of things to the right of that, as we already discussed in figure 6.
Hmm.
But the point of starting there is that that's really the rate of growth that we expect for the brightest progenitors. And that shape is not consistent with what we see in the data.
Correct.
So there are lots of now, so those little blue points are some recent data, all have spectroscopy, things
Oh,
around redshift 3 and 4.
okay.
Um,
Oh,
all
these.
over the place, right? Which is what you expect, of course. There are
Yeah.
going to be galaxies of all masses at all redshifts. And those could be plausibly explained by those red dashed lines from the simulation.
Yeah.
But those then would be the progenitors of low redshift ellipticals, right?
Yeah.
They're going to build up a lot.
Typicals, yes.
But, that doesn't do anything to explain the higher redshift data.
Correct.
Right.
Yeah.
So to explain the higher redshift data, you need something like those solid lines, which are the monolithic models I
Okay.
mentioned early on.
Okay.
And those TI is half zero point 4, zero point 0.3 gigayears. Those basically things that formed 300, 400, 500 million years after the Big Bang. And remember, that's what Sanders had predicted, that a 10
Yep.
to the 11 solar mass galaxy would take about 500 million, 600 million years to expand and contract.
Yes, it
So those
does.
monolithic lines are good proxies for what you expect in MOND.
Cool.
Have some of the mass manages to form a population of massive galaxies early on. And, we're seeing them have a lot of stars because there are a lot of stars there. The mass was assembled
Yes.
early. And like I say, in order to explain that with lambda CDM, we have to turn those dashed lines into those solid lines or, something similar.
Get there somehow. Hmm.
Now, of course, it's only a subset of galaxies that become massive early. Presumably, the descendants of those are giant elliptical galaxies. Spiral galaxies, as we know, have a more continuous star formation history.
Hmm.
You can explain that easily in either paradigm. So you'll see a
Right.
dotted line there
Yes, this
cutting
black
through
one.
where the red lines are. Yeah, that's
Black one. Yeah, yeah.
basically a spiral galaxy model with a much longer attenuation time scale, right?
Oh,
So
sure.
those
Yeah, yeah.
solid lines have very short
Okay.
quenching time scales. If it's a much longer time, then you get a much more gradual growth.
Yeah.
And so, yeah, it's fine to see things like that, and it's easy to imagine that something like Andromeda is trailing along that kind of line and ends up being around 10 to the 11 now, but
Uh-huh.
wasn't at redshift 4. Uh, But what's really hard to do in the lambda CDM models is those massive high redshift things,
Yes.
and that happens naturally in MOND. That's exactly what Bob predicted and what I found as well, and what other people has found as well. So um, that happens on other scales too. So the last figure,
Let's see. Figure
figure
11.
11. So
Yeah.
this goes back to
Possible solutions.
it's a ways down, yeah.
Yeah. Good. There's a
To J.
discussion
Frank's
going
thesis
on.
again. Remember, he was looking for protoclusters, identifying such things.
Just to make the point of it. Should form. Okay. And figure
Yeah,
11, last figure.
it should happen. What we're seeing is what was predicted. And let me go back because right, we mostly have talked about lambda CDM because
Yes.
we really, in order
Right.
to
So we do.
compare theses, we need a prior, we need a prediction. And so, the prediction of these simulations that existed falls short. We can tweak it. Okay, fine. We can then ask how
Jiggle.
plausible that is, and that's what most of the discussion has been.
Right. We can jiggle those things.
So we haven't, all we've said is that, well, geez, Bob Sanders predicted it, and now we see it. And that's kind of the problem with having a successful prediction. There's not much more to say than that. Um, it's really remarkable, though, how often does it happen in the history of science that you make a prediction like this a quarter century in advance
Okay.
of the observation corroborating it?
Not often. Not often.
Yeah, it's a really amazing thing. And so we should take a moment to appreciate that.
Appreciate that.
Right or wrong, we need to understand why that happens. Why does Mon have the predictive success
And
that it
there's the
does?
rub, right? So we see
Yeah,
it,
yeah,
but why?
but why? And so we can talk about that at great
Sure.
length, but one has to start, I think, by respecting the scientific
Observations.
method, and
Yep.
that's what was predicted.
Yep.
Um,
Cool. Okay.
So another prediction was that,
Mm.
well, everything forms fast. So the
Yes.
accelerated structure formation isn't specific to galaxy scales. It goes up to larger scales. And so clusters of galaxies are bigger. So they should
These
take
are, oh, these are
a
data
couple
clusters.
gigayears to form.
Okay. Okay.
And
Hmm.
Jay was simply looking for protoclusters, things that might
Yes.
become
Yes.
clusters at
Yes.
low redshift.
Yeah. Hence the
And
name.
so that's what's shown here is,
Uh,
when you identify a clump of galaxies in both position and redshift space, well, the velocity dispersion comes for free, right? You have the redshift of a bunch of things, so you can just measure the velocity dispersion. And so that's what's plotted as a function of redshift.
hmm.
Each point is one cluster. The size and coloration reflects how likely we estimated the cluster was. So
Got
J,
it.
an algorithm that finds
Got it.
things, and also assigned a probability to whether or not they're real.
Okay.
So in a nutshell, the light gray things probably are not real.
Yes.
The light blue things, could be.
Probably.
Dark blue things, oh yeah,
That's
definitely.
real. Okay.
And those have at
Wow.
least 10 spectroscopically confirmed redshift members all right there. So as well as
So
however many
dispersions.
galaxies were around
500,
it, there are at least 10 with
600.
spectra right on top of
Okay.
each.
Okay.
So those biggest, darkest points are the most robust. And you can see there are some at redshift 2, a few at redshift 3, maybe even a couple of redshift 4.
Right.
And that's a couple of years after the Big Bang.
Right.
That's how long it takes.
And it's a relatively flat
And there is no clear indication of mass evolution. That's right.
evolution. Okay, flat, flat. Yes.
Or velocity dispersion evolution.
Yes. Fair enough.
And I don't comment here on the conventional masses because Jay did that already in one of his papers.
Mm.
But a result to be aware of in that context, and conventionally in terms of lambda CDM, we don't even expect these things to
It
have
wouldn't
settled
be
down.
there.
So,
Yes.
so the
Yep.
first thing is we don't believe the masses, right?
Okay.
Because they're still coming together.
Fair
So
enough.
what Jay also did was look at the Millennium simulation again and look at those things that matched, right? He applied the algorithm. He did find protoclusters in the Millennium simulation. And then you can ask, what's the velocity dispersion of those things?
Uh-huh.
And they run consistently a factor of 2 lower than what we observe.
Uh-huh. Mm-hmm.
Right. So as well as there being an
Mm-hmm.
excess light problem, there is an excess velocity
Velocity
dispersion
dispersion
problem.
problem. Yes.
And that the velocity dispersions we're seeing here, typically 600 kilometers a second, are higher than similar objects in the simulation.
Cool.
Um, and so I here just ask myself, okay, well, maybe these things have already formed in Mond, and I'm not sure that's true at all, but the time
It
scale
is.
is about right. And so on the right axis is the corresponding mass that you would infer in Mond.
Yep.
And those are sort of reasonable for rich clusters at low redshift. 10 to the
Mm-hmm.
14th solar masses would be a big rich cluster today.
Mm-hmm.
So maybe. But of course, the point is that the prediction happens on all scales. And so you should even get really large things like what Tolley has discovered with Laniakea and
Yeah.
things like that.
Mm-hmm.
It
Okay.
just keeps going. So
Cool.
let's just go through the conclusions, shall we? See if I
Sure. And then
remembered everything.
okay.
So section 8.1 is just deals with the photometric evidence. So I've broken this up
Several years.
into pieces. And so basically, I think what's well established at that point is point one is that galaxies are brighter at high redshift than we really expected.
Yeah.
Um, and that again
That's
is
fair.
comparing to contemporaneous models, not what's been tweaked once we see the answer.
Right.
There seems to be a population of massive galaxies. Not everything at high redshift has to be massive. It's just that there's at least a
Sure.
population of
It is.
L-star smash things that are already in place, certainly by redshift 3.
Mm-hmm.
And the things that we're seeing at redshift 10 are consistent with being the progenitors of that. If they're just, the traditional, you formed a galaxy, not a whole bunch of little proto-galaxies that are still assembling, but you
Yeah,
got
yeah.
basically a galaxy there.
Yep.
That's not to say that merging doesn't happen at late times. It's
I'm sure
just
it
that
does.
most of the mass assembly for this population seems to be done already at this
Yes.
point. Um,
Interesting.
and so the evolution of the stars is really consistent with old stellar populations. And, the existence of these bright galaxies at high redshift is consistent with what Mond predicted, not with what lambda CDM predicted.
Fair enough.
So that was the photometric evidence, the kinematic evidence,
Yes.
right? So again, there's evidence that things formed early, and it's worth noting what the contemporaneous prediction of lambda CDM was. So Sanders 1998, same year that Mo, Mao, and White 1998 was published, and that's a really important touchstone in lambda CDM galaxy formation theory.
Okay.
And so, and Ho-Jun Mo was my office mate as a postdoc. He's
Eh,
really excellent. I believe what he says when he says, and what he said at the time was that it took a long time to assemble disks. Disk galaxies didn't just appear. You have to have all these things assemble, and you have to not mess up the disk along the
pretty
way.
much. Right.
And so you don't really expect them to emerge until after redshift 1. That was the contemporaneous prediction when Bob was saying, geez, you might make galaxies at Z of 10. And I noted some of these individuals. We do see galaxies at 5 and 6 that are already apparently rotating disks. They're just anecdotal individuals so far. But these are crazy high velocities that we see. They're
Yeah.
rotating disks, with 200, 250 kilometer a second rotation speed. That requires a lot of mass, right? You have to
Yes.
have assembled a lot of stuff together already.
Yes.
And that is not, sort of the hierarchical picture.
Hmm.
Um, and moreover, we see these relations, both Tully-Fisher and the dark matter
Dark
fraction surface
fraction.
brightness relation. And
Yeah.
so whatever physics established those relations, it seems to have established them very early on, and then they're just there.
Yes.
Um, so we need to understand that. Now, again, that doesn't sit comfortably with a hierarchical model in which you're building everything up gradually.
Right.
Um, but it's quite natural in Mond because these relations are imposed by the hypothesized force law of Mond.
Yes.
It would be there from the beginning because the force law says so.
Cool.
And so what are the last things I say? And
Structure
this sort of
formation.
the referee kindly nagged me to say things what will happen at higher redshift. And it's like, ain't it enough to predict redshift 10?
Ah,
You
speculate, speculate. Come on, come on,
gotta
speculate.
walk a mile in this universe. But of course, one wants to think about what's going on. And so something I
Prediction.
did predict myself,
Yes.
motivated by Bob's work, was
Yes.
that reionization would happen early.
Early, early, early.
So we know it's over by redshift 6.5 or so, and we're starting to have constraints on how it built up. But the nominal expectation in Lambda CDM was that it should happen after redshift 10, maybe 11. In Mond, it should happen earlier than that. So I say here Z of 12. That's a fairly conservative statement. My best guess be redshift 17.
Okay.
It could
Okay.
be earlier, it could be best, and right time is really compressed in there, so it's plus or minus a lot. But that's my best guess. Going back to a paper I wrote 20 years ago.
Mm-hmm.
So that is an expectation. Now, reionization in this stage, I think, will be slow and patchy. It's going to rely
Sure.
on normal stars that are forming early in these sort of, in this sort of accelerated way that we've been talking about. But I don't think you're going to get a big boost from top heavy IMFs,
Okay.
top three stars.
Mm-hmm.
You do have to
Take a
form
normal.
quasars very early on, which is a challenge all by itself. But what MON does for one is form structure early. And so you get going on this early. So I think
Yes.
cosmic dawn and reionization
Gonna
got
be formed
started at
better.
higher redshift.
Cool.
Um, Obviously, massive galaxies should form above redshift 10 to indulge the referee's requests. I do think it should be hierarchical. It's just that hierarchy is greatly compressed in time.
Yes. Sure.
So there's a whole lot of chaos that's going on at redshift 15, right? So you will see those little chunks of things assembling and so forth. But it's just that you've already managed to assemble some of them into
Right.
big
To
things
get the
by
build.
redshift 10.
Fair enough.
And same thing for clusters as we just discussed. Those should form
You
pretty
go on.
early on. Um, you should have an enhanced integrated Sachs-Wolf effect.
Ah, okay.
That is to say,
Yeah, yeah.
you've got structure forming earlier, so that should be correlated with structure along the line of sight. There are some indications of that in the literature, and nobody believes them because it's way too much.
Okay.
So whether it's right for this or we just shouldn't believe it, I don't know. Um,
It's there. Okay.
One of the things that MOND simulations are good at doing is sweeping the voids clean. This is something I know Jim Peoples worried
Mm,
about a lot.
right.
The voids are not just empty, but they're too empty
Yeah.
for most hierarchical simulations. It's really hard to do a MOND simulation, so I had a try at this. Other people, Hadi Nasser, others since then have worked on this. And again, something that's fairly consistent is you sweep the voids pretty clean. Not 100% clean, of course, but pretty empty, and you do that pretty early. Um,
Sure.
Takes longer, of course, because we're talking about a larger scale. So maybe redshift one, redshift a half, something like
Okay.
that.
Okay.
And there's a nice illustration of that in the 2015 paper that I did a review for this. And again, historically, when I wrote that review in 2015 for a Canadian Journal of Physics, um, I had in mind that JWST was coming up. So I wanted to remind everybody of these predictions, which were already very old at that time. And now that's a decade ago. So, it
Wow,
takes
they're really
time.
old.
Yeah. Um, and
Cool.
one of the things that's really scary to me, because in order to have this discussion, you have to be able to hold in your mind completely inconsistent thoughts. And so, I understand lambda CDM pretty well. At heart, I'm more comfortable wearing that traditional dark matter hat.
Mm-hmm.
I understand how it should work. But if you want to talk about Mond, you have to take that hat off. And then when you put on the Mond hat, there are a whole different set of assumptions, and
Yep.
that includes what you assume to be known. So conventionally in cosmology, we know for sure that the cosmological principle holds,
Okay.
right? The universe has to be uniform and homogeneous.
Mm-hmm.
And so when
Assumption.
people like Shrekar at Oxford started reporting that, gee, maybe we're seeing an anisotropy in the expansion rate, I'm like,
Yeah,
no way, that can't be true. Um, but maybe it is. I mean,
it is.
I had mentioned Jim Felton had first done this solution that Bob used to
Yeah.
as the top hat galaxy formation scenario. Felton had tried to apply it to the entire universe. And one of the things that he found was
Okay.
that you really would have a hard time
Okay.
maintaining isotropy at late times in a
Yeah.
universe defined by Mond.
Okay.
Now that depends on the dark energy. Um, he didn't know about that at the time, though he did consider it in other papers. But if there is nothing like dark energy that tries to make the expansion rate accelerate, then
Right.
you basically, by late times in a purely Mondian universe, would have a pretty far departure from isotropy. It would be kind of fractal.
Okay.
Uh,
Sure.
if you do have dark energy, then that fights
Good.
with Mon trying to make everything into a fractal, and
Ooh.
you do reach an isotropy scale, which Bob estimated in one of his papers to be around 300 megaparsecs. I
Okay.
forget the
Oh,
exact
hey.
number.
That sounds familiar.
And that depends very sensitively on what the baryon density is, because it's basically just baryons fighting against whatever the dark energy is. So, that is something to look forward to, I think, if we can get enough measurements of not just redshifts, but proper distance indicators over enough of the sky that we can start to map out if the expansion is really isotropic or not.
Good.
And I would assume it is, but the universe
Test
has
it.
surprised
Test
it
it.
before. So
Test it.
um, that's an example of something to look forward to.
Cool. Very cool. Stacy, I want to thank you so much for walking us through your very awesome APJ article.
Well, thank you. And I know it's a hard subject for people to wrap their heads around. I still struggle with that after having worked on it for many years. But the bottom line to me is the application of the scientific method. We
Mhm.
were able to predict this with this crazy theory of Milgram's, and he's had a long series of successful predictions, of which this is just the latest. So that's got to be telling us something, right?
Telling us something. I don't know what it's telling us, but it's telling
Exactly.
us something.
I don't know. And so Judy Young, Vera's daughter, once made to me the analogy of the blind man and the elephant. And I do think that's appropriate here, is that, we're feeling different parts of the problem. And, okay, this end is dark matter, or this end is a strong, whatever. And we have yet to assemble that into a coherent whole. And so I think that's really encouraging because it means not all answers have been, not all problems have been solved. There's
Yeah,
still some
we don't know
science to be
everything yet.
done. And it's fundamental science, right? It's not just,
Oh, yeah,
oh, we're going to detect the dark matter and then we know everything, or oh, we have to tweak this star formation model. There are fundamental issues. Does the dark matter even exist?
correct.
Do we understand gravity well enough to be talking about these things? So science is not over, and I find that very, very encouraging.
Phew, that's good. Very cool. Well, let me ask something along that line, since you mentioned it a couple of times. Kind of in the short term, where do you think we go from here, given the published article? Do you anticipate there'll be 10 times as many galaxies coming from JWST over the next couple of years? Just sort of next steps. Where do you think we go?
Right. So absolutely, I hope so. I think, people are going to continue using JWST to make these surveys and to find things. And so, that figure six had a lot of extremal statistics in it. What is the most massive thing you see? How often are we going to get that? At some point we will have surveyed enough of the sky that
Yes.
we've either found out, oh, we hit a rich vein to begin with, or no, that's just what
The
the
way it is.
average chunk of the universe looks like. So,
Yep. Yep.
um, there's just looking for things. Then there's spectroscopic follow-up. We're always going to be ahead of the curve with photometric redshifts
Always.
because of the way the
Faster.
technology works.
Right.
But so we want to follow that up with spectroscopy and
Neat.
measure these things. Kinematics, right? So, we talked about Tully Fisher and things that does not yet extend to as high redshift. And so, I look forward to
Filling that
finding
in. Yeah.
things and measuring things and hopefully enough things that we can define Tully Fisher out to a higher redshift and do it in a self-consistent way. One technical challenge to appreciate is that at low redshift, we can detect the 21 centimeter, which typically extends out beyond the optical edge of the disk. So we can
Yes.
see a nice clean V flat going indefinitely far out.
Mm-hmm.
Um,
Mm-hmm. Yes.
at high redshift, we're usually using H alpha, which is restricted to
Uh,
the optical disks, or
mm,
some molecular tracer via
oh,
ALMA,
yes.
which also tends to be
In
restricted
the
to the
disc.
optical disks.
Yeah.
So one has to be really careful about comparing apples with apples
Yeah.
in this game, as well as the stellar evolution. I mean, what Mon predicts is that there should be a baryonic Tully-Fisher relation. And so you have to account for the mass in stars, not just the light, and you have to account for, whatever gas might be present. And
Yeah.
we can do that with models and scaling relations and so forth, but it's always going to be a dodgy proposition, right?
Okay.
There's
Cool.
a lot to be explored there yet. But again, predictions and say the prediction of Mond is that there's a force law that is imposed by nature. So these relations, like Tully Fisher, are going to be imprinted on galaxies from the beginning. In
Primarily.
lambda CDM, you still have to have a hierarchical formation paradigm.
Oh,
So if that's the explanation, I would expect to see these relations to sort of emerge, organically somehow from
really.
this process of
Yes.
assembly. And so, once we get to high enough redshift, then they shouldn't be there in such a emergent
Fair
picture.
enough.
And I'll leave it to the simulators to tell me when they predict that would be.
Fair enough. Very cool. Very cool. Stacy, I want to thank you so much. That was really awesome. Thank you so much.
Oh, sure. It's
It'd be
fun to talk
really,
about,
it'd
right?
be really exciting to see this develop over the next couple of years. I mean, it's been an exciting the past couple of years been really exciting in this field. It'd be really exciting to see it go forward in the next couple of years.
Yeah, the fire hose continues
Yes.
full tilt. So,
Yes, it does.
well, thanks
All
so
right.
much. It's been fun talking about it. I really
Sure.
enjoyed it. Yeah.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Ciao.